Okay, so 0.5 milliampere flowing here, no current goes here, the same current comes here, and 0.5 into 5 is 2.5 volts across this. So if this is 5 volt, we further drop by 2.5 volt to get 2.5 volts as V2. So no current flows here, we get this to as 2.5 volts. So this is at 2.5 volts, at 2.5 volts. This is 0, so we can very easily find this current. 2.5 minus 0 over 2.5, which is 1 milliampere. No current can go or flow here, so all this current is coming from here. 1 milliampere current comes from here, and the direction says this will be the polarity across this 10k resistors, and we will have 10 volts across this. 1 into 10, 10 volts. This is at 2.5 volt. The lower potential is 2.5 volts, so higher potential would be 12.5 volts. And we can find this current. This current would be 12.5 minus 0 over 1, which will be 12.5 milliamperes. And we have 1 milliampere current going here, 12.5 going here, both outwards. So KCL is going to find this current to be 13.5 milliamperes. So a 13.5 milliampere current flowing through a 3 kilo ohm resistor is going to get 13.5 into 3, a voltage of 39 plus 1.5, that is 40.5 volts. And if 40.5 volts in this polarity. So if this is the lower potential is at 12.5 volt, the higher potential is going to get 52 plus 1, 53 volts. Here is a catch. Opamp output cannot be outside this range. So 53 volts here is not possible. So VO2 will actually be saturated at plus 20 volts. So you see, if the supply voltages are given, you have to be very careful about this. Look at this, minus 5 volts, it's still in this range. So this is okay, this is operating in the linear region, but this is not operating in the linear region, it is saturated. And this is in the linear region. So while we have found VO1 and VO2, we still have to find IO1. So this will be at 20 volts. 20 volts minus 5 volts, so a current would flow this way, and that would be 20 minus 5 over 15. So that is 25 over 15. That would be 5 by 3 milliampere. This is at 5 volts, so we can find this current. 5 minus 0 over 2, which is 2.5 milliamperes. No current can go in the op-amp from the input terminal. So 2.5 milliampere is actually coming through this source. This source has 2.5 milliampere flowing through it as well. So we have this current coming from here, this current going here, and so this current is going to be IO1 is the outward current plus this outward current must be equal to this inward current, which is 5 over 3 milliamperes. So IO1 would be, this would be 1.666 minus 2.5. So 1.667 minus 2.5 milliampere is going to be IO1. And similarly, we have IO2, which is the outward current. So we can write the normal way, negative of IO2 is outward, and we take outward currents as positive as over convention, plus 13.5 plus 5 by 3 is equal to 0. So IO2 is minus 13.5 minus 1.667 milliampere, whatever that may be. So this IO2 is found by exploiting these currents. But here is the catch. The catch is if VO2 is 20 volts, since this op-amp is no longer operating in the linear region, it's in saturation, so all these characteristics do not hold. So there may be some current going in here. So actually, once you have found an op-amp to be in saturation, you cannot apply ideal op-amp characteristics at the input. And that's basically jeopardize this whole thing. So once you write that this is in saturation, we know we cannot for sure tell this current or this current or this current or these voltages, and because we don't know what the internal circuitry of the op-amp is. So whatever we are sure is about this voltage, and that's it. We are not even sure about this current or this current. So you have to write here the op-amp number, op-amp 2 in saturation means ideal op-amp characteristics cannot be applied to its input terminals. Hence, value of IO2 and even IO1 cannot be assessed. So I've just solved it in detail so that if both had been in linear region, you know how to solve it, and you can see that it's not a very difficult circuit to solve.